Hi, welcome to the second session of double sequences and double series. In the first session, we defined the notion of a double sequence and talked about iterated limits and convergence of a double sequence. Okay, and then we also proved when those three concepts are equal. Okay, then later we define the notion of a double sum, double series associated to a double sequence. There also we define three sums, two iterated sums and one double sum. So today the main result is going to be under what conditions we can say these three sums are equal, that is two iterated sums and the double sum when they are equal. Then we will apply this to prove if a function is defined by a power series which is convergent on a positive disk of convergence, okay, then this function is going to be analytic in the disk of convergence. In fact, I started this series only to prove this crucial result. Okay, yeah, okay, let us get moving. So the first thing we would like to prove is a very small proposition. Okay, suppose AMN is a double sequence and AMs are all positive, and let us look at AMN, right? And then we want to say this is this double sequence, double series AMN. Notice that when I write this means double sum. Okay, this is convergent if and only if the partial sums Smn equal to summation Aij, j equal to 1 to n, I equal to 1 to m, okay, is bounded above. Maybe you say R bounded above. That means there exists C positive, so that Smn is less than or equal to C for all m and n. Okay, this is the result we want to prove. Call it if you want lemma. Okay, notice that this is we have an analog in the infinite series. If ANs are positive, then this is convergent if and only if the sequence of partial sums is bounded above. Okay, these are analogous result in the theory of infinite series. Okay, now the proof, let us go through. Okay, so let us assume C is such that Smn are less than or equal to C for all m and n. Okay, we want to prove that double series AMN is convergent. Okay, right? So what is that I want to show? If I want to show this is convergent, then what I have to do is I have to find an A such that AMN equal to A, right? And this what was the definition? The definition was for every epsilon positive there exists n, so that for all m n greater than or equal to n, mod s mn minus A is less than epsilon, right? So how to find that A? Now again go back to this analogous case. If ANs are positive and if this is convergent, if only if this is bounded above, right? And when notice that Sn is a monotone sequence, so if it is bounded above, you want to say Sn is convergent. Where does it converge to? It converges to LUB of Sn. Okay, right? Recall that. That gives us an idea what. Okay, let A equal to LUB of Sn. Yes, Mn. Okay, M n vary over n. Right? Okay, let us see whether it converges. Right? Now, since suppose epsilon is given, okay, then a minus epsilon is less than a, therefore a minus epsilon is not an upper bound of SMN, right? Therefore there exists Iij said that, let us look at the picture. This is my a, this is a minus epsilon, there exists an Sij here. Sij is greater than a minus epsilon, right? Now let n equal to maximum of I and j, right? Now let any m and n be greater than or equal to n. What is the relation between Smn and Sij? Okay, and see this mn and greater than or equal to n, therefore m is greater than or equal to I, and j is also greater than or equal to, n is also greater than or equal to I. Okay, is greater than or equal to n and hence greater than or equal to I, j. Are you following? M is greater than or equal to n, therefore it's greater than or equal to I. And n is greater than or equal to n, and therefore it's greater than or equal to j, right? Therefore, so to Smn I am adding a few more non-negative terms to Sij to get Smn. Therefore Smn is greater than or equal to Sij, right? Therefore where will I find my Sij? Smns I will find here, right? But notice that Smns are bounded by A. Therefore what do I have? So I have the following result. Therefore for all m n greater than or equal to n, Smn, okay, is greater than a minus epsilon and less than or equal to a and hence less than a plus epsilon. That means for all mn and greater than or equal to n, the distance between Smn minus a is less than epsilon. So hence conclude Smn is convergent and hence this mn amn is nothing other than LUB of Smn. This is exactly analogous to infinite series, ordinary infinite series. Okay, right, pause, review, proceed. Now let's look at the converse. Converse is easy. So what do we have? AMN I want to look at, and I am given AMNs are positive, and suppose it's convergent. If it is convergent, then the sequence of partial sums Smn is convergent, right? Okay, and hence it's bounded. In particular, bounded above. Yeah. If you don't like this, let us do in a slightly different way. Right. Suppose this is convergent. Okay. Right. If this is convergent, then this sequence, let us call it a Tn, or let us say Bn equal to Snn. Then this is Bn is convergent. The diagonal sequence is convergent, right? We had already seen this. Where did we see this? See, this is how I just reflect. So that, okay, do you remember? Yeah, when you wanted to prove, we define the notion of a Cauchy sequence, right? And Cauchy, I mean, when I say double sequence is Cauchy, then we wanted to say a double sequence is Cauchy is convergent. How did we use that? We looked at the diagonal sequence and we said that it depends only on n, and it is ordinary Cauchy sequence of complex numbers, therefore it's convergent, etc., etc. Do you remember? See, this is how this kind of going back and forth is the one which makes you understand mathematics as a whole, and you don't have to remember a lot of things. Slowly, it becomes part of you, like the way multiplication table becomes part of you. Okay, so So come back to this. So right now, is it okay? What am I supposed to show? I want to show it's bounded, right? Now this SNN is convergent, therefore SNN, notice that is already non-negative, therefore let's say equal to some capital S. Okay, maybe capital S equal to supremum of SNN, that is LUB of SNN. Okay, right. Now start with any INJ, right? So Sij is less than equal to SKK, where K is maximum of INJ, right? Because you are adding some more positive sums, positive numbers, but that's less than equal to S. Therefore, I have shown the sequence Sij is bounded above. Okay, pause, review, proceed. Okay, and now comes the next lemma. Okay, so let us again assume AM is a double sequence. Okay, right? Then let us look at three iterated sums. If you want, you can also assume non-negative. Okay, without that, I will simply say AMN. This is over n, this is over m, and this is again this interchanged n and m mod AMN, and this is a double sum AMN. So as I said, if I assume this is non-negative, then I don't need to put modulus. Okay, I say one of the above sums exists if and only if all exist. Okay, so let us try to understand what it says. It says that if one of the iterated sum exists, the other iterated sum exists, and the double sum also exists. That is, they are all convergent, it exists. See, for example, if I write summation m followed by and summation m, then summation n modulus amn is convergent. That means summation n or mod amn for each m is convergent. So call it alpha m. Then summation m over alpha m is convergent. Do you follow that? That is, if I put alpha m equal to summation amn, this is over n. Okay, if I say this is convergent, I'm just going slow so that you should not get worked up. Okay, you should not simply assume things are right, but you should understand the statement. Okay, if this is convergent, and then summation alpha m is convergent. This is what it says. Then what do you want to conclude? You want to conclude summation a mn modulus over m. This is convergent, therefore call it beta n, and then beta n is convergent. And the third, what it says is, let us put tmn equal to summation I and summation over j equal to 1 to n, I equal to 1 to m of mod aij, then tmn is convergent. That means this double sum is convergent. Okay, please take some time, review the concepts, understand. So simply don't, you have some kind of a vague feeling it's correct and then go ahead. Okay, don't do that. Okay, pause some time, review, and then proceed. So let us start with the proof. So let us assume that double summation AMN is convergent, modulus is convergent, right? And notice that we already know if TMN is the partial sums of this, then the sum A is nothing other than LEB of TMN. Okay, this we have seen from the last lemma, right? Okay. Now I want to prove one. We will prove one iterated sum exists. Okay, we want to prove that, right? Okay. Now fix m. Now let's look at I equal to 1 to m of mod a I j equal to 1 to n. Yeah, but this is nothing other than tmn, right? And therefore this is less than or equal to a, right? Therefore fix m and let n tend to infinity. This means I equal to 1 to m and j equal to 1 to infinity of mod a j. This is true for all n, right? So forget this. Now let's concentrate on this. Okay, this is true for all this. If you want, even fix an m and just look at this only. J equal to 1 to n mod a j, but that's less than or equal to tmn. Okay, that's less than or equal to a, therefore this is less than or equal to a, right? A. Therefore letting n tend to infinity, because this partial sums of this is bounded above by a, therefore I know it is convergent, right? Summation j equal to 1 to infinity of mod a j exists. Okay, call it equal to alpha. This is m, sorry. Fix an m, so alpha m exists, right? This is true for all m now, right? Now let's look at for I equal to 1 to m and j equal to 1 to n of mod a j. As I said, is less than or equal to tmn, that's less than or equal to a, but this is a partial sum. This is less than or equal to your alpha I, right? You follow that? Therefore this fellow is less than or equal to summation I equal to 1 to m. Notice that for a fixed I mod a j equal to 1 to n is the partial sum of the series, and it converges to alpha I, which is the LUB of the partial sums. You understand? Therefore each one of this less than or equal to alpha I. Okay, therefore I have I equal to 1 to m of alpha I is less than or equal to a. This means summation alpha I 1 to infinity converges. Okay, pause, review, proceed. The other iterated limit is similar. Similarly proved. Okay, so what have you shown? I have shown that if the double series is convergent, then both the iterated series converge. Okay, one I proved, the other one is similar. Now the other way around. Okay, conversely, let us assume summation over m, summation over n of mod a means convergent. So we have to prove whether this is convergent. Yeah, yeah. So what is that I have to do to prove this conversion? Okay, notice that I have to say if I put tmn equal to summation ij mod I equal to 1 to m, j equal to 1 to n, okay, then I have to prove tmn is bounded above, right? Now notice that this fellow is less than equal to I equal to 1 to m. Yeah. Since I know this series in conversion, that means first of all this is conversion. Okay. And if I call it alpha m, therefore this term is less than equal to alpha m. Yeah. But this is less than equal to summation I equal to 1 to infinity of alpha m, because this is conversion. Right? The iterated series is conversion. That means this is conversion. Okay. Call it alpha. Therefore what I have shown is Kmn is bounded above by alpha. What is alpha? Alpha is the sum. Okay. Now you can ask, I assumed one of the iterated sum exists and hence a double sum exists. Okay. Now notice that when a double sum exists, both the iterated limits exist. Therefore, if one of the iterated limit exists, the second iterated limit also, second iterated sum also exists. Do you follow this logic? Okay, pause. Okay. First understand this PRP. What I have shown is, if this exists, then I proved this exists. Okay. From the first part, this shows the second thing also exists. If double sum exists, we showed that iterated limits also exist. Therefore, the second iterated limits exist. Therefore, we have proved completely whatever we wanted. Make sure that you understand. Okay. If one of the three sums, there is two iterated sums and one double sum. If of absolute terms, if one of them exists, all other two exist. Have you understood? Right. What is the natural question you should ask now? Question to ask, under the hypothesis of the lemma, can we conclude further, namely, you understand that? Okay, we conclude that if one of the sums exists, all other two sums also exist. But are the sums equal? That's a very natural question, right? Okay. So we are going to answer it in the next theorem. That's the theorem. We are going to prove it. Then we want to conclude the following. M over n of am n equal to the double sum amn, which is equal to the other way, the iterated sum amn. What does it mean? If I want to find Just just think about it. Just don't go into the proof quickly. What it wants to say. So the question is, given a double sequence, we have defined associated double series. And for that, we have defined the notions of three sums, two iterated sums and one double sum. Okay. And we may want to know, given a double series, I want to know whether it's convergent or whether what is it a sum. What we know is again mathematics. If I know how to sum as ordinary infinite series, summation n equal to 1 to infinity of an. Okay. Okay. Whereas the double series is something slightly more involved notion, the sum of a double series. So what it says is, under some favorable conditions, okay, to find the sum of a double series, that is so-called, just like that, let me call it double sum of a double series is nothing other than iterated sum, because I know how to sum summation n equal to 1 to infinity of amn, call it alpha m, then I know how to sum summation m equal to 1 to infinity of alpha m. Okay, so I found the double sum. Okay, is that clear? And notice that under stated condition it says each of these three sums, two iterated sums and one double sum, they all exist and they are all equal. That also part of the theorem. So try to understand, the statement looks very simple, but it tries to convey a lot more. Okay. Now suppose the theorem is proved. Does it answer my earlier question? Yes. Why? Suppose AMNs are non-negative. Okay. Then one of these iterated sums or double sum, summation AMN are okay. Now this without modular sign, if AMs are non-negative, if they converge, okay, we know that all of them converge, right? Under that condition, the conclusion of the theorem says these sums are equal. Are you following? Just pause to think. So our question is answered. This theorem answers our earlier questions. Right? Just make sure you understand this. Okay, let's try to prove this. So I hope you understood the last result. That's the main result. See, the same thing as in integration. You define the notion of double integral f of xy dx dy. Okay, it may be difficult to compute, but we know using our integration is anti-differentiation kind of idea. Okay, I know how to integrate f of xy dy. Okay, now I get a function of x, then I know again how to integrate it with respect to x, right? So I reduce it to iterated integral. The same trick it says. Okay, and in analysis you will see many of the times you want to interchange the order of integration, order of summation, etc. This theorem gives a specific sufficient condition. Okay, this is actually a special case of Fubini-Tonelli theorem, which you learn in product measures in measure theory. But that is immaterial, just ignore. Okay, we will give direct proof here. Okay, right. So let us go ahead. So proof. In view of lemma, in view of the earlier lemma, we said if one of them exists, all three exist, right? Now what is the hypothesis? It says one of them exists. Therefore, I can as well assume that double sum exists. We may as well assume the hypothesis is this. Because remember, hypothesis says one of them exists, but the previous lemma says all three exist. Therefore, I can as well assume that my hypothesis that double sum exists. Is that clear? Okay. Right. Now, so again, the earlier lemma said if this double sum exists, this exists. It looks repetitive, but notice that this exists. So this in particular implies, this is an infinite leap actually, but this in particular implies AMN modulus over n exists, right? This in particular, this implies AMN, if it's absolutely convergent, this series is convergent, this exists. Do all of you understand this? Okay. Now let's look at. So what do I want to say? I am going to show. Okay. Now notice that this exists. Sorry. I'm sorry. We know this exists, right? Okay. This implies this exists. Exists. Okay. Because if the double series is absolutely convergent, then it is convergent. Okay. I do not know whether I proved it, so let me just make a proof. Implies this exists. Okay. So this is yet another lemma. I forgot whether I proved in the last lecture, but let me just quickly do that. That's very easy. So let the Tmn be the partial sums of this, Smn the partial sums of this double series, right? Then what do I have to show? Smn converges. Right? So it's enough if I prove Smn is Cauchy. This again we have said, a double sequence. Okay, if it is Cauchy, it is convergent. Okay, so let us prove that. But that is very easy. The exactly the same way is the analogous case. Smn. Okay, suppose R and S is greater than or equal to m and n. Notice that what is our definition? R is greater than equal to m, S is greater than equal to n. There let me write S or S. Oh, maybe R and T, because this S may coincide S and T minus S mn. Okay, right? This is less than equal to T R S minus T. Sorry, T R. Oh, again, that's not a good thing. Let me write. Sorry, let me just change the notation. So let m be greater than equal to I, n be greater than equal to j. Then let me look at S m n minus Sij. Okay, but this is less than equal to T mn minus Tij. Okay, this is again the analogous case in one variable. If summation mod an is convergent, then summation an is convergent. So let Tn be the partial sums of mod an and Sn be the partial sums of an. Then Sn minus Sm modulus is less than equal to Tn minus Tm. But since this is convergent, that means this is Cauchy, therefore this converges to 0. Therefore this is also Cauchy. Right? The same proof here. Okay. This implies since the Tmn is Cauchy, Smn is Cauchy. How do you write the proof? I hope all of you know. Okay. There exists capital N so that m is greater than equal to n. N is m is greater than equal to I is and I is greater than equal to n is greater than equal to j is greater than equal to n. Then Smn minus Sij, that is Tmn minus Tij is less than epsilon. Given epsilon positive, this Cauchy, this sequence is Cauchy, implies there exists n such that for all m and n and I and j such that m is greater than equal to I is greater than equal to n is greater than equal to j is greater than equal to n, mod Tmn minus Tij is less than epsilon. But actually Tmn will be greater than equal to Tij, therefore there is no modulus. Okay, so the result follows. Okay, I'm sorry. Okay, this is a very typical result, so I don't want to spend much time. Okay, now go back. So what did I want to do? Yeah, I wanted to show. I almost forgot what I wanted to show. Let me go back. Suppose this is given. This is my hypothesis. Okay, so therefore this implies summation AMN is convergent. Right? Okay. So I want to show this is good. So now next thing is this implies, as I said, AMN over N, this is convergent. Right? Since this is convergent, right? So let sigma M equal to I equal to 1 to M and J equal to 1 to infinity of AIN. Do you understand what it means? So I have A11, A12, etc. plus AM1 plus AM2, etc. Okay. This I know this is convergent. This is convergent, right? So this is convergent. Okay. So what all I have to prove? This is convergent for every M. Therefore, when I write I equal to 1 to M, then this is a algebra convergence series. Okay. If this is equal to something alpha M, this will be equal to alpha 1 to alpha M. This object. Yeah. Okay. So to prove the result, what I have to do? I have to prove sigma M converges to the double sum. So let S equal to the double sum AMN. Okay. I have to prove this. If I prove that, what does it mean? This double sum AMN equal to, this is the 1 to infinity, 1 to infinity. So I have proved this result. Do you follow that? Okay. So how do I do that? Since, see, let SMN be the partial sums. Yeah. Therefore, what I know is SMN converges to yes. Okay. Now what I want to claim? I want to claim my sigma M converges to yes. So let epsilon be given. Since SMN converges to yes, this means there exists an N, so that for all M, N greater than equal to N, mod SMN minus S is less than epsilon. Right? So what does this mean? This means summation over I equal to 1 to M, summation over J equal to 1 to N of Aij minus S is less than epsilon. Right? This is true for all M, N greater than equal to N. Yeah. Now what do? You fix M. Okay. And let N tend to infinity. So this will mean I equal to 1 to M of J equal to 1 to infinity of Aij minus S is less than equal to epsilon. Yeah. Are you following? Okay. Right. So, but what is this? This is nothing other than your sigma M minus S is less than epsilon fiction for all M greater than equal to N. I proved sigma M minus S is less than equal to epsilon. That means sigma M converges to S. That means this iterated sum equal to the double sum Aij. See, these things may look like magic, but go through that carefully, you will understand better. Hi. So next we will give an application to the power series as we said.